Good morning, everyone. I'm Emma Bunce, and I'm the President of the Royal Astronomical Society. I'm pleased to be with you this morning to introduce Professor Yvonne Elsworth as the 2020 recipient of the Royal Astronomical Society's Gold Medal in Geophysics, to present today her Gold Medal Plenary Lecture here at NAM. As I mentioned yesterday, the Gold Medal is the Society's highest honour and usually recognises extraordinary contributions to research or leadership, and often an individual's outstanding lifetime achievement. The medal was first awarded in 1824, and past winners of our most prestigious award on the geophysics side include Harold Jeffreys, Sidney Chapman, Hans Alfvén, and James Van Allen. Professor Yvonne Elsworth is a pioneer in solar physics, with her outstanding achievements in helioseismology revealing fundamental insights into the structure and dynamics of the solar interior. Her technical expertise, dedication, and exceptional leadership over many years have been instrumental in the success of the Birmingham Solar Oscillations Network, known as BISON, and in realising the full potential of helioseismology, which we're going to hear more about today. In addition to her exceptional research, throughout her distinguished career, Professor Elsworth has played a prominent role in shaping policy and management of astronomy, both in the UK and internationally. She was elected a Fellow of the Royal Society in 2015. Professor Elsworth was the first woman appointed to the prestigious Poynting Chair at Birmingham. The lasting influence of her work is the improved gender balance in astronomy and in the personal advancement of women scientists, whom she has so actively supported. Professor Elsworth has made an extraordinarily rich set of contributions to our understanding of solar physics, and through research and policy leadership, both nationally and internationally. I'm delighted to introduce Professor Elsworth now to present the Gold Medal Plenary Lecture entitled The Benefits of a Slow, Steady Heartbeat. Over to you, Yvonne.
Thank you. Thank you for those wonderful words. I don't entirely recognise myself, but that's fine. Okay, so it's a great pleasure to be able to talk to you about the research that I've done. In the nature of things, I'm concentrating largely on the past here. A slow, steady heartbeat is a more popular name for helio and astroseismology, the study of the sun, helio, and astroseismology, i.e. the sort of vibrations, the waves. And I'll try and give you some historical context, the odd link to Bath, and one or two of the key results that have come out, so that you can gain, I hope, some sort of understanding as to why this topic, which started off very small in the 1970s, 1980s, and has now become something that is so important, and particularly for stars, so widely applied by many, many, many people. Obviously, when one talks about the sun, one can have the pleasure of looking back at some beautiful items, and I'll start with one that is 1350 BC or so, they think. Nordic Bronze Age mythology. The picture comes from the National Museum of Denmark, and it shows you the classical view that something had to move the sun across the sky, and putting it on a chariot and horses was, what people were used to, so that's what you actually decided. No one knows quite what the purpose of this particular item was. The reverse side of it does not have the gold on it, so it was obviously designed to be looked at from one side. You can build your mythology around it, but I can't tell you more about it. One can then move on to Apollo. Now everyone knows about Apollo, the sun god, known as Phoebus or Bright. He also drove his chariot across the sky, and you can see here it's a 4-horse chariot. That was the real elite chariot that people had. It's also interesting that he was the god of music, and we'll see that there are musical analogies right through this topic. That's people making an attempt out of what they knew to give you a framework for how something worked. That's pretty good scientific method, really. Okay, so we can now think, all right, the weather's nice and warm now, or very warm, depending on your opinion on it. Nice place for a holiday. So William Herschel, of fame of Bath, in about 1780, and I quote, is believed to have considered the sun to be a cool, dark, solid globe, clothed in luxurious vegetation and richly stored with inhabitants, protected by a cloud canopy from the intolerable glare of the upper luminous region. I've taken this from a brilliant paper that I can recommend people to read by Koala and Verwerke on the habitable sun. You might look at this right now and think, that's crazy. How on earth did he think that? But you have to remember that at this time, it's not that long since the mercury and glass thermometer had been invented by Fahrenheit, the Fahrenheit scale. And actually, I think most at this stage, many of the planets were believed to be inhabited. There was a concept that, that human beings weren't localized to the Earth. And that, again, is something that there are real resonances for in the modern world. We think this method, this idea, clearly doesn't work, but it took improvements in physics and observations in the 19th century and methods of measuring temperatures to give a more sensible deduction that the sun is a vast ball of hot gas. So how do you measure the temperature of the sun? I mean, you might have your mercury and glass thermometer, but you can't go over and just shove it into the sun. You have to do remote observations. And Fraunhofer was very important with his method of measuring temperature. But it took some time after that before people had a decent solar model. It took significant advances in theory and quantum mechanics to begin to understand how things might actually be. And we move through now to Sir Arthur Eddington from Cambridge. And we have on the right-hand side the classic Renaissance-type picture of a man, usually a man with his tools of his trade. The one thing you might notice if you've seen other photographs of Eddington is that he wore glasses. I don't know whether the photographer said take off your glasses or whether he preferred himself photographed without them. But anyway, there should be sunglasses. There should be glasses on him. Anyway, his view was actually the deep interior of the sun and the stars is less accessible to scientific investigation than any other region in the universe. Right now, this is a time when they're beginning to build cosmology, and he thinks that in the interior of stars and the sun is impossible to observe. He wasn't giving up on the process of trying to understand what was going on. His view was what you needed was theory. Theory would enable you to take what you could see on the surface and build a model for the interior. And that clearly is of great fundamental importance. But if we now fast forward to 1970, 1980, we get the philosophy that you can study the interior of the sun and many other stars with the help of resonant sound waves in their interior. Now, stars that oscillate with large amplitude had been known for some time, but there was absolutely no expectation that stars like the sun would show oscillations, and these oscillations are anything but easy to detect. The typical motion on the surface of the sun is a few centimeters per second. Right now, this work was first being pioneered at a stage when people thought that kilometers per second was a really good measurement. So there was a huge job to do initially, just to convince people that actually this wasn't just an artifact, an observational artifact. There are known to be waves in the atmosphere where we're just distorted by the atmosphere. Well, the way to prove that was to go to more than one site and demonstrate that you could get the same data from two well-separated sites. And this was done. For stars, which we'll come on to later, stars other than the sun, what we're talking about is micromagnitudes. So again, very, very difficult from the ground. We'll see that the real breakthrough, the technological breakthrough, came with satellite measurements. But for the sun, a single object, we can measure in radial velocity, and we can measure radial velocities centimeter per second, even millimeter per second level. Put that into the context of the speed of light, and you can see that we're into part in 10 to the 10, part in 10 to the 11, which is an explanation why the original name for the group in Birmingham was high resolution spectroscopy. It wasn't known as the solar group at all. The work was started by George Isaac in Birmingham and other people around the world, but Birmingham was one of the pioneers in this. And what George wanted to do was measure the motion of stars with planets around them. He wanted to detect extrasolar planets. So he started with a measurement on the star that we knew, with planets that we knew, and he started on the sun and expected to find the effect of Jupiter and all the other planets on it, but Jupiter and the moon, big pull. And in the process, he discovered something else. So we believe that the sun resonates like a musical instrument, the whole volume of the sun. I say the whole volume of the sun is responding to sound waves, pressure waves, but clearly the picture I've shown you of modes in the sun and the different colors are Doppler shift, plus and minus. You can see that this particular mode does not occupy the whole volume of the sun, doesn't see the poles, it doesn't go into the center, and it's got a complex structure on the surface. So some modes are really quite localized within the sun, but others of them sense the whole volume of the sun. And it's those modes that we've concentrated on in Birmingham, where we take the sun as a single point, a pixel. Now we end up with a little bit of imaging because of Doppler effects, but essentially we're integrating the light from the whole sun as opposed to putting a camera on it and resolving the mode structure, which is clearly also possible. Okay, so we have our musical analog here, and we say, okay, you play a note, you play A or whatever. When you listen to it, you can make a good bet as to whether you're listening to a double bass or a flute. So the question is, how do you know? What is it that tells you that that's true? And the answer is harmonics. You don't get the pure note from the instrument, you get a harmonic structure, and that harmonic structure is quite characteristic of the instrument. So also when I talk about the sun resonating as a musical instrument, I'm not talking about getting one pure note out of it, I'm getting a complex structure, both with spatial distribution, but also an overtone structure. And that is incredibly powerful. So the simple statement is that the sun oscillates at a period of about 5 minutes, quite slow, quite regular. It's not the fundamental mode. The fundamental mode is down at an hour or so. And it's believed that convection is what drives, it's the noisy, turbulent environment that actually drives the oscillations. You think about a kettle boiling, you can tell when it's almost boiling because the convection gets really vigorous and you can hear it. That's what we're talking about in the sun. And you can see a sunspot there, nice and dark in the center. And you can see perhaps how Herschel thought that that was giving you a look into a cool space underneath. We now know that it's still rather toasty, and that it's just relatively cool. Nothing in absolute terms. Not suitable for human beings. Okay, so we can talk about sound waves, we can talk about sound rays, and I'm going to show you a picture of some rays, artist's impression clearly, very schematic drawing. But what it does is it shows you several things. So waves travel to different depths in the sun, and they also come to the surface more or less frequently. So the waves that don't go in very far are the ones that skip along the surface and have a complex structure on the surface, or a detailed structure, high resolution structure. And the ones that are going into the interior don't come to the surface very often. So that's why when you don't image, you see those modes. You can also see little stripes across the, there we go, along the ray. And these are wavefronts, again estimated. The speed of sound varies substantially through the volume of the sun. And this, these lines tell you something about how the sound speed is varying. So you can see that it's anything but uniform. So you can compare this with models, and I would say that the models are good, not to say superb. But there are two issues here. One is the data have phenomenal precision, and therefore you can't get away with a 10% sort of view. The data really nail the theory. And that's one of the things that's quite exciting as an observer and an instrument builder, is that you, in many ways, are in the driving seat. But the other issue is that there's a lot of physics that's not well understood. And I'm not going to discuss it in any detail, but there are, for instance, big question marks about the composition of the sun. Now, what you have to remember in all these is that we're trying to get the sun's, the knowledge, the mapping of the interior of the sun and the matching to the physics very, very precisely, very accurately, because from this, we're going to extrapolate to many other very different kinds of stars. So the sun is the thing that we can get really good measurement on, and we're going to extrapolate. So we have to be very sure that we know what we're doing. So to summarize, when seeing standing sound waves in the sun, resonant interactions, so we're going to see modes. The red waves are the ones that skip around the edges, and they give you a complex pattern on the surface that's known as medium degree. To observe these, you need an imager. You need to be able to resolve the surface. The waves that go into the interior, and it's very hard here to draw the simple breathing mode, the L equals 0 mode. So we haven't got that on there, but very low degree modes probe the interior. And if you want to know about the interior, you have to observe the low degree modes. Okay, so where do we collect the data? Well, we can start on the roof of the physical, whoops, moving through, starting to go through its own speed. We can collect the data in Birmingham, and we have got a dome on the top of the physics building in Birmingham. In the background, you can see Joe, the clock, built to provide public time, so it's visible over a huge area of Birmingham. That is our test bed. It's very convenient, but as you saw when the picture bounced through, that it sometimes rains in Birmingham. And also the sky, even when you think it's beautiful, by the standards of good observatory sites, it's rubbish. So it also has the disadvantage of all single sites that the sun rises and sets. So we are this thing is starting to go through at its own speed, so I'm going to be ending up going backwards from time to time. We set up a network, and as Emma said, it's called the Birmingham Solar Oscillations Network. We were told we had to have an acronym, so we had an acronym, and we chose BISON partly because it fits very nicely, but partly also because the great rivals at the time were an American group, and we were told we couldn't survive against American competition, and the bison were hunted to extinction over the American plains. Okay, so we have 6 sites, we ignore Birmingham for this process, placed around the world so that we have coverage in longitude so that the sun doesn't set on us. It also gives us north and south hemisphere so that we get different weather climates, different weather patterns. We tend, although it's not entirely true, we tend to be at observatories. The one slight exception to this is Western Australia, Carnarvon, where we were on a radio site rather than, and it's now closed down, rather than an observatory that does optical work. But you can see our various sites down there. We have pioneered the control of instrumentation via small computers, starting with the BBC computer and moving on to more and more powerful machines as this happens. Originally, the data got posted back. Now it comes back over the internet. But it is all automated, controlled from Birmingham, and makes a lot of decisions for itself. The whole philosophy of keeping things like this working is that you have to report faults before they're faults. And so there's a whole lecture to be given on how on earth you do this. And actually, we're now moving with the go-to amateur telescopes to actually changing even our footprint so that we can consider being not in a relatively expensive, large, by our standards, dome, but in a really small, localized construction. But as I say, that's another subject. Okay, so what I really wanted to talk about was the oscillations. Many, many ways to use the data, but I'm concentrating on the frequency of the modes. So here is a typical spectrum. Once you get past a couple of years, it actually is impossible to tell one spectrum from another until you actively analyze it. So what can we see here? The peak is around 3,000 microhertz, 5 minutes, as I said. These are low degree modes because we've got a global view of the sun. We're at a high order, we're not at the fundamental. There's obviously a range on here, but the central ones are around an order of 21. But you can also take some things very visually from here. If you look to the low frequency end, you can see, the amplitudes are smaller, but from the cutaway, you can see that the modes are really quite narrow. And I'll come back to the comment on rotation in a minute. If you go to the high frequency end, you begin to get merging of modes because the lines are very wide. And this is basically the influence of the turbulent surface and the fact that the higher degree modes are more located within that turbulent region, whereas the low frequency ones have their top point of their cavity, their upper turning point is lower, and so they're less sensitive. If I go back to the left-hand side, and you can see that there's a splitting of this mode into components, and that is telling you about the rotation of the sun. You have to go down to these low frequency modes because clearly you couldn't tell anything like this out of the wide ones, but this was one of the fundamental measurements that we made, because here we're not measuring just the surface rotation of the sun, we're measuring the volume of the sun. And so it really begins to tell you about the rotation rate in the deep interior, an integrated value, the outer layers, but also the deep interior. And that was an important discovery. Okay, so if I home in on just the central part of that spectrum, So you can clearly see the modes that we have there. So L equals 0 is the breathing mode, is the one that has no angular structure. Close by it is an L equals 2, which is an octopole mode. We can see L equals a quadrupole mode, sorry. Between the L equals 0s, you can see an L equals 1, so dipole mode, and tucked in beside it, the L equals 3. And you can see that there's a repeat structure here. So there's an L equals 1 at the beginning, we go through a 2, 0, an L equals 1, 2, 0, and so on, so that I can indicate that there's this typical spacing between modes of the same degree, and I've marked L equals 1 here. That is a function of the mean density of the star. So when you have that measure, you have the mean density. The other important parameter is the 0-2 splitting, which is actually dependent on the conditions in the core of the sun, in the center of the sun. And that was, again, led us to one of the key discoveries from Birmingham. So the small spacing between L equals 0 and L equals 2, a measure of core conditions. And in the early 90s, there was the huge problem that the number of neutrinos measured from the sun was too low. And the current thinking was, well, the conditions in the center of the sun are pretty tricky. We ain't got that right. But what we did was to produce a very precise measurement of this and demonstrate that you would have to change the solar model beyond recognition to get any agreement with the neutrino problem being a solar problem. So we showed that the solar models were really, really rather good, and hence the neutrino problem was not a problem for solar physics, but was a problem for particle physics. And okay, why might it have been a solar problem? Because people don't believe solar theory. At least particle physicists tend to believe the solutions lie in particle physics. And eventually it was discovered that there was a very small amount of mass associated with the neutrinos, and they could change their flavor as they came out of the sun, and all the problems were solved. And actually it's a pretty important discovery. Okay, one of the other things I wanted to talk about was the active sun. Our sun is not quiet and boring. It is very active, sometimes more active than others. It has spots on the surface, as we've discussed. Sometimes it's pretty sparse like this. Other times there's rather more activity. You can see this lovely, lovely picture from Hinode with the Earth in top right-hand corner as a scale. So these are fairly large objects. Magnetic field is controlling them. You can see the bubbling convection all around. Convection cells have a turnover time of 5 minutes. That's what matches the solar oscillations. And strong magnetic fields all over the sun. So this is a measure of the magnetic field strengths around. There's a huge topic of discussion here, which I'm not really going into at all. But sunspots have strong magnetic fields in them, and that's what makes them, relatively speaking, dark. Okay, so we can go back in history for a minute. Spots were observed. Fabricius, 1609, he observed the spots and he saw they moved, and he interpreted them, and we think correctly, in terms of evidence for a rotating sun. The publication reference, private publication, June 1611. I guess he wrote a letter to somebody and said, I've seen this and this is how I understand it. More famously, perhaps, Galileo and Scheiner also made the observations. Galileo, great fame. Scheiner was a Jesuit, and he observed them and was basically told they were spots in front of his eyes and go and improve your glasses, mate. The sun was considered to be perfect, unblemished, and sunspots were considered to be a blemish. There's also the period of the Morton minimum, where there were very few spots from 1645 to 1715. We're grateful for the fact there were observations before. There are much earlier Chinese observations where they just observed through cloud, and heaven knows how many people's eyes got damaged in the process, but we know there was a period where there were very few spots. And William Herschel, again, to give him slightly better press, he actually showed that there was a good correlation between high grain prices, data from Adam Smith, correlated with a spot-free sun. So he was beginning to show that the weather in the Northern Hemisphere, particularly Northern European Hemisphere, has some correlation with solar activity. The understanding for that requires you to understand transport through our atmosphere, and again is way outside my scope. So Schwab found in 1843 that it wasn't just, well, sometimes there are spots and sometimes there aren't. He discovered that the number of spots was cyclical, and this is the solar cycle, and the Royal Astronomical Society gave him the gold medal for this. Slightly later on, but a similar time, Carrington measured the positions of spots and set up the notion of Carrington rotations, which we still use today. So how many times has the sun rotated since Carrington labeled this point is 0? He was an amateur, extremely good, but an amateur. And some of you may know the word Carrington in terms of brewers. So he had to stop in 1861 when his father died, and he had to go and run the family business. So we have the fact that sunspots vary with time. There's actually a magnetic cycle, which is twice as long as the cycle if you just count sunspots. So there's a 20-year cycle with field reversals every 11 years. That's something that people would really rather like to understand and explain. Again, a nice topic. Okay, so this is the solar cycle's sunspot number, nothing to do with oscillations yet, where we're showing cycles 23, 24, and a prediction for 25. So from just essentially through this 2000 on. You can see that people have predictions. Predictions are not always accurate. This prediction was actually released in the end of 2019, so the sun hadn't quite gone through its minimum. You can see that the spots, the sunspot number at maximum is changing, so the sun is becoming quieter. There's also structure at the maximum, which is well known in many activity measures. So the previous maximum is the smallest, so cycle 24, the smallest for 80 years, and the activity is much like it was over 100 years ago when the sun went through a quiet period. If you're interested in seeing any of these, the references up on the top of the page there, it's really very interesting to see that not only do we have this 11 or 22-year cycle, but we have other very much longer cycles. We shall see whether or not the next cycle is of the right size, the same size. We think it probably will be, but there's always the question as to whether the sun is going to head into another Morton minimum. Okay, so that's counting sunspots, which has been done for a very long time. How do the measured oscillation frequencies respond to the solar activity cycle? They increase the frequencies with solar activity. They're believed to be due to near-surface influences. So we expect modes that have more presence in the near surface to be more strongly impacted. What we're measuring is about a 1 second change in the sound travel time, which is around the sun, which is about 6,000 seconds. So we're looking for a part in 6,000 change. And we're looking to try and correlate it with various activity indices. The correlations are good, but not perfect. You choose one in one cycle, and another cycle, another one has a slightly better correlation. Interesting. And we have some evidence that both the localized strong fields, the ones that sit in the sunspots, are important, but also the distributed network weak field is also important. So I wanted to show you the early data that we went to press on this, partly for students, postdocs, early postdocs present, just to show you how apparently rubbish early breakthrough data appear. So what you have on the left-hand side is the shift we got in frequencies. The different symbols are different L values, and put on top of that in the dotted line is the sunspot number. The right-hand side is the correlation. There are clear correlations. We waited very carefully until past the minimum and the signal began to rise again, because clearly when it's only falling, it's a bit tricky to be sure. You can also see that the density of the spots is going up. We started to have many more stations around the world. The network started to work. So we had the confidence to go to press on this. You also notice that we made a mistake in the Julian date. We should have written modified Julian date. We got serious flack from people for not putting in modified. So that was cycle 21, early data, and at a level controversial, but nevertheless statistically very significant. I show you the modern data, and you would ask me, why was there ever a question? So the point I wanted to make was early breakthrough data. You have to be clear on your statistics, you have to believe your uncertainties, but always looks a bit dubious, or can look a bit dubious. So there are several things to look at in this picture here. We've plotted the solar data, the oscillations data in the black signal, in the black symbols with dots and uncertainties. You can see that we've also got a red line, a dotted line, a dashed line, and a dot-dashed line. They are various activity indices, radio flux, magnetic fields, sunspot number, and calcium K, which is an activity index that you can measure for distant stars, which is really useful. You can very clearly see the reducing variation in the activity. You can also see that if you look at the minima between the cycles, so between 22 and 23 and 23 and 24, there's quite a divergence between the measures. We very clearly see the double bump at the top of the activity cycle, but we also see evidence for continuing structure at the bottom. So there's a question here as to whether, because we're seeing under the surface of the sun, we're seeing a buried dynamo as opposed to what the surface oscillations will show you. There's also evidence for a shorter term periodicity of about 2 years, most marked on the falling phase of cycle 23. We go through here a big bump, and some evidence for the structure down the bottom. As I said, new data is never as clear cut as when everybody can observe it and it's entirely straightforward. Maybe this is just an artifact. It's a continuing topic of research for us. We're also, I'll show you some later data in just a minute, but we're also to the stage where we now have data through 4 solar cycles. So one of the questions that we're currently investigating is, can we see the magnetic cycle? We can clearly see the sunspot cycle, but can we tell the difference between one magnetic cycle and the next? I can't answer that question for you right now. Okay, so I remind you about the typical spectrum. And the fact that the higher degree modes turn higher in the sun and are more sensitive to the turbulent surface. The lower degree modes, the lower order modes, the lower order modes are less sensitive and therefore less responsive to the solar activity cycle, which is localized at the surface. So what we expect to see is, if we divide this spectrum up into bands, that we will see more activity influence at high frequency and less as we go down. So what I have here is very recent data that shows you two of the bands, not the very lowest one, and you can see very clearly that there is a change in the response at the different frequencies. I should add here that clearly COVID has impacted our ability to observe, and it's a testament to automation, but also to the dedication of the people who help us run at the various sites, that we are still on air, report that mistakes, that faults have been corrected, and although our data flow is not quite what it was, we can still show you solar activity measures. So these are data that we're currently looking at. We'll take it back to the other solar cycles as well. We have I think it's 45-year spectrum that we're currently playing with. Okay, I'm going to have to speed up. So solar rotation, the sun rotates.
Just to give you 5 minutes.
Yeah, the sun rotates roughly every 25 days. There's differential rotation in the convection zone and transition below that to an inner region. So here's a map that doesn't have solar oscillations from us in it, and it has to stop when you get just into the core. You can very clearly see the differential solar rotation, but they can't tell you what's going on in the interior. If I add our data, what it says to you is the interior of the sun is rotating as a solid body. Interesting. Okay, so the pulsation timescale is dependent on the mean density, and this has been known for some time, and you can estimate the period from the sound crossing time. The fundamental for the sun, as I said, is about 1 hour. If you get to bigger stars, it's much slower, and if you combine the separation with where the frequency at which the oscillations peak, you can measure the mass and radius. And oscillations are ubiquitous, many, many types of stars. But my particular interest is in stars that are red giant stars like the sun, and some slightly more massive stars than the sun become. The Kepler mission, in its various forms, was designed to look for exoplanets, but NASA were convinced that the same data could be used for solar oscillations, and what's more, when they find planets, and we had to promise not to find planets, when you find planets, you can measure something about the host star. You can measure its mass and radius, and that's fundamentally important. So we were given free proprietary access to the data set. Absolutely fantastic. 4-year data set from the best of Kepler. It's a huge asset and has opened up an enormous set of data. As they say, other products are available. Corot, French ESA mission predated Kepler and produced some lovely stuff, but it was low. It was in a low Earth orbit rather than an Earth trailing orbit, so it went through the radiation belts, and so it's really quite, the data are not as good. And there's TESS that's currently up, still collecting data, but it's looking at the whole sky and moving around. You get about 80 days spectra out of it. Very good, but not the same as Kepler. So what happens to stars as they age? A, they get bigger, conditions inside change, and very importantly, at some point they start to burn helium as well as hydrogen. And that's the point we'd like to know. So I have a series of spectra from Kepler here, starting at the top with a star like the sun, and moving down to a very luminous red giant. And you can very clearly see that the spacing changes, that the frequency at which they're centered changes, and what you can't actually see is that the oscillations get stronger as you go down. But we start with micromagnitudes. Micromagnitudes in a period of a few hours, impossible to do from the ground. What you need is tranquility and continuity of space. I should show just one of the stars that had a rocky planet, just because that was what gave us access to the Kepler data. A little bit lower frequency than the sun, about 1.5 times the sun. but not orbiting once a year, but orbiting 2.8 days. It's a distance of 4.3% of the Earth-Sun distance. Not what one might expect. So there's a whole exoplanet topic here. I said that we want to know when helium is detected. You can't tell it easily from models because the spread due to mass and metallicity overlaps the region where stars move from igniting helium in their cores, either explosively or not, and move down. That's a fundamental point in a stellar model. Very, very tricky to observe traditionally. But you can do it with the astroseismology. And you do it what are called mixed modes, modes that are sensitive to both the core and the outer regions. And these give you a very clear measure of essentially whether the oscillations are in the core or excluded from the core. And that is basically telling you whether or not the core is burning helium or is not burning helium. So we've detected that. We can measure the rotation rate. Now you might think as stars get older, they differentiate, the envelopes expand, cores contract. So you expect that the spin rate of the interior goes up. Absolutely what we see, not what we see in the sun. And the centers are rotating really very fast. Again, angular momentum transfer in stars not well understood. The fact that you can make measurements of the interior core rotation rate is absolutely fundamental. So, very exciting times. You can see there are many, many topics here that I can't discuss, but it's other people's forte rather than mine. But that there have been huge fields opened up by this ability to measure the interior behavior of stars and not just rely on theory. I should finish with a modern impression as to how the sun might really work, courtesy of a cartoonist, which says there's a chap sitting in there and he's reading the Sun, not the Sun Times, I can't remember which one it is, the Sun Chronicle perhaps. So he sits there, he's pretty warm, but he raises the lever and lowers the lever and the sun does as it's told. Lawson is the man's name. So thank you very much, and I'm happy to take questions.
Professor Elsworth, thank you so much. That was a wonderful talk. It was really, really inspiring and interesting. I particularly enjoyed the starting off point where we had the idea of the sun as being pulled across the sky by chariots, as an enthusiasm of horses and solar terrestrial physics that brought together lots of my enthusiasms into one graphic. So thank you for talking about that. And also the connection to Bath as well. Thinking about, I can just imagine the conversations in the Herschel household and the imagination that they had to be thinking about the sun as habitable. If you were to ask most people today where would be the least habitable place, they'd probably pick the surface of the sun. So to think about the imagination of people that would actually be thinking of that as a habitable region, it's astonishing, really. It's really, really interesting to think. And I think it's hearing about those sorts of questions that people were asking in the past makes you realize what really drives our science forward. It's by asking those right questions and having the imagination. So thank you for that historical perspective as well. I'm going to move across now to look at the question session and to see what we have from people. We have one from Liam Edwards. What causes the double bump feature in the solar cycle peak? So question is, what causes the double bump in the solar cycle?
I don't know. At the maximum, it's extremely well known, extremely well observed. I don't know the answer. What I do know is that the solar oscillations follow it. And if I speak now just as a solar oscillations person, there is there is one scenario, which may be wrong, which says that not only do you have a deep-seated dynamo that drives the 11-year cycle, but that you have a surface dynamo which runs with some linkages to it, because it'll influence the transport of flux through the surface. But that has a 2-year cycle. Okay, so one explanation which has been put forward is that there is this surface dynamo with a period of about 2 years. Again, not absolute, not a sharp line, but roughly speaking 2 years. And if that's true, then all the other activity measures should follow it, because they're looking at the sort of surface effects of the dynamo, the magnetic flux that you measure, the interaction with the radio signal for the 10.7 radio flux, and all these surface measures, these external measures, stop when you don't have surface magnetism. But the solar oscillations, because they're sensitive below the surface, should retain some sensitivity to it. And hence, we think we see a continuation of the 2-year signal through the minimum. But, it's somewhat controversial, and the signal to noise is not brilliant. But as I showed you in the original data, if you wait for perfect signal to noise, you don't make any breakthrough. But that's my best understanding of it.
Thank you. It struck me when you were giving your talk that you have to be very patient to be a solar physicist when you're actually looking for multiple solar cycles, don't you, from data? So that's it's something that it certainly requires levels of, I suppose, not just patience, but also creativity in how you actually approach the data analysis. There's a huge amount of technique in there, as well as the actual science questions themselves.
The other huge problem is keeping funding, where you can't say I'll get a result next week, when you have to say, well, I need 11 years of data, and so we are very grateful for the community that supported the running of Bison, and we run on a shoestring, an absolute shoestring, and most of we now have a bit of analysis funding, but most of the analysis funding we have is done on the back of techniques that we develop in a stellar context, where the stellar context has European funding and space agency funding, but funding with long-term stuff is just so tricky.
It is, and I think one of the things that's come about in recent years has been this understanding that as we start to look at things, for example, like the effects of the sun on our climate, our long-term climate, that the need for those long-term data sets becomes apparent sometimes a long time after you actually had funding to collect them. And so that continuity of funding is something that's really, really important for our community. I'm going to ask a question related to your observatory network now, which comes from Vicky Scowcroft, which is how often do you actually have suitable observing conditions? And I think that really relates to your Birmingham campus observations.
Well, the weather in Birmingham is quite nice. I mean, I wouldn't knock Birmingham. The problem actually is the atmosphere and the pollutants, I guess, in the atmosphere. We do have, didn't produce it today, but we do have spectra that come from Birmingham. And if you compare it with the high Andes, then, you just can't, you just don't get the signal to noise. So it's not really a matter of just the sunshine in Birmingham. Yeah, the sun shines in Birmingham, it's a lovely place, but it doesn't have the atmosphere, sadly.
Just related to that, this might be a bit of a naive question, but I'll ask it anyway. Have you had much change because of the lockdown involved with COVID and the lack of, I suppose, so much pollution from traffic and so on? Have you seen much change in your observations from that?
It's something we look for, and I'll come back to that point in a minute, because we also look at volcanoes, the eruptions of big volcanoes, and we can absolutely see that, because out of our data, out of just the intensity measure, we get a measure of how clear the atmosphere is, what the extinction is. We look for the effect of COVID. The problem we have is that when COVID first hit, almost everything closed down, and so we actually have a gap.
Okay.
But longer term effects, because we did get things running again. As I say, the observatory people have been stunning, plus automation. I mean, the fact that when we change things from Birmingham, we upgrade things from Birmingham. The software is very simple, but very sophisticated. And great thanks to our, the technical team. But we don't have data from the absolutely low bit of the atmosphere.
Okay. Yeah. It'd be interesting to know, I guess there's going to be decades of scientific studies on atmospheric data based upon this period of time. So I guess there's lots and lots of data to pull that with. Another question I'm going to put up now, which is the sun close enough to a pure sphere that any oblateness can be ignored, even at the quality of today's models and observations? And what about other stars?
Okay, well, other stars vary enormously depending how fast they're rotating. So there are some fast rotating stars where your models of the modes that you expect, you have to take into account the oblateness. There is an oblateness measurement for the sun, or there are oblateness measurements. The effect is not strong enough to change the characteristic of the frequencies. What I will say is there's an American group it's done from space and from ground, who resolve the surface of the sun and so measure the high resolution, high surface variation modes. And there's some evidence that the distribution of the differential rotation has changed recently.
Okay.
So if I get it right, the upper layers of the sun are going around slightly more slowly than we used to.
Okay.
So although the oblateness itself, which is tiny, is measurable, it doesn't change my understanding of the modes, but the differential rotation itself is very interesting. And is that telling us about real fundamental changes? Is it related to the fact that the solar cycle is much smaller than recent cycles? I don't know.
Thank you. Chris Lee, next. We have a question which is, thank you for the fabulous mix of science and history. What might we expect, if anything, from future observations of the ESA SOIO in this
solar
seismology
orbiter, I think he might well mean. One of the interesting things for our stuff, for the results, for the unresolved sun deep modes, probably nothing. But they are making measurements as they go through their paths, their transits around the sun, of the higher degree modes. And one of the things that's really interesting is everything we do is in the plane of the solar system. Now, solar orbiter is going to go higher latitude, so it's beginning to get a view of the pole. Now, you have radial oscillations, and they're transverse when you're in the plane of the ecliptic, and they're at the surface, the poles. So I would expect us to get some interesting measurements on higher latitudes and some more constraints as to what's happening there.
Thank you. A very quick one as well. You mentioned about the fundamental mode being a 1 hour period, and but then you had a very, very strong peak at the 5 minutes. Why was it at 5 minutes particularly?
Because the disturbance that drives the oscillations is convection. The convection cell turnover time is about 5 minutes.
Okay.
And so that's where the driving is strongest. So the fundamental will be there, but incredibly difficult to measure because the amplitude of it, the interaction of it with the convection layer, the outer convection layer, will be very small. And it's one of our goals to work down towards it. We can get down to about n equals 8 at the moment, and that's millimeter per second. But the great advantage is that the modes are very long-lived down there. So if you get a very long spectrum, you can coherently add all the data, but you're looking for a spike. You're looking for a needle in a haystack. So that's the reason for it. And it's related also to the what's called the acoustic cutover of frequency. And that's partly why the frequency at which you see the modes peak is part of what gives you an understanding of the radius and mass of the star. It's together with the spacing between the large spacing. But essentially, your question is absolutely fundamental. That's important. It's the interaction with convection.
Thank you. Thanks very much. We have another question from Janet Bowie asking, have solar magnetic field reversals given any insight into terrestrial field reversals, which occur every few million years? That's a great one, isn't it?
Outside my information, my knowledge. I mean, clearly, if you study dynamos, then it's nice to have an Earth one and a Sun one, but as I understand it, they're really rather different.
I think it's something that is it really piques the public understanding in our area. One of the questions is, what's going to get us first in solar terrestrial space weather physics? Will it be a big meteor hitting the Earth, or will it be the magnetic field reversals? How will they affect us? All these different questions that happen on different timescales, and I think it's something that does really enthuse people and excite them about our field sometimes when they realise that something very, very exciting will happen eventually in this area. So we've got another question coming in. I think this is probably going to be the last one because we're almost out of time. You mentioned that the frequency shift of the solar activity is caused by surface effects. How is it possible to exclude effects around the tachocline, e.g. stronger magnetic field, lower gas pressure, higher sound speed?
Okay, it's a good question. The tachocline, named by Douglas Goff, is essentially where you move from differential rotation to solid body rotation. A region of very high shear. Don't know that we actually know how narrow it really is because it's quite tricky to measure. The reason I say it's the surface is because of the way different modes are influenced. That makes us think that the main effect is localized at the surface. I don't have time to go into the whole of it, but it is essentially because different frequencies and different orders and different degrees respond differently, and therefore you can drive that back to believing that it's very much in the surface. That is not to say that there isn't an effect, as Tom says, related to the tachocline, but it's hard to explain what we currently can observe in terms of a deep effect rather than a surface effect.
Thank you. So I think we are just about out of time. Just remains for me to thank all of the people that have posed such excellent questions for this plenary talk, and mainly a huge thank you to Professor Elsworth for a really interesting and inspiring talk. And I think that if more people hear talks like that, we'll have a lot of very good people entering the field of solar physics in the future. So thank you, Professor Elsworth. And we're going to conclude the plenary now. Thank you.
Okay, thank you very much. Bye-bye.
Bye-bye.